I'm Mani Khanuja, Principal Generative AI Specialist Solutions Architect at AWS and author of 2 books on building these systems in production. Last time we found that your model runs in 2 completely different ways, and I promised we'd get precise about the numbers, so bring your dashboard to this one because we're going to read it together. Here's the situation I want to put you in. Every graph on your screen is green. Your latency is inside the target you agreed with your product team, and your users are quietly leaving. So, how does that happen? It happens because the obvious way to measure this is also the way that hides it. So, today isn't about new metrics for you to memorize, it's the ones you already have measured so they catch what's going wrong. Let's bring back that timeline from episode 1 and we'll relabel it fast, 1 line each, because you already own all 4 of these. Time to first token is your queue plus your prefill. Inter-token latency is the gap between one token and the next one. Throughput is your whole system, every request together. And goodput counts only the requests that arrived early enough to still be worth something to the person waiting. That's the vocabulary which we learned back in episode 1. Today is a different problem because measuring those 4 the obvious way will tell you everything is fine while your users might be leaving or complaining. So let's put 2 more names onto that same picture, the 2 that episode 1 didn't cover. The first is TPOT, time per output token, and you can remember that one as TPOT. So what is it? You take one request, take all the time it spent generating, and divide that by how many tokens it produced, one number per request. The second is E2EL, end-to-end latency, the whole thing from your request arriving to your last token leaving. Now, what should you notice about TPOT? Episode 1 gave you inter-token latency as an idea, the gap between one token and the next, and TPOT is the number your monitoring is plotting on the wall right now. Those 2 sound like the same idea. They are not the same number. So what is TPOT not? It isn't the gap between 2 tokens. It's the average of all of them. And an average has already thrown away the thing you came looking for. So here's the whole episode in 1 line. TPOT is an average. Inter-token latency is a distribution. And a stall, the moment your user's screen freezes in the middle of a sentence, is a tail event, which means it happens to some of your tokens some of the time, while all the rest of them are perfectly fine. So what does an average do to a tail event? It dilutes it. That's the whole job of an average, right? Which means your stall is invisible at the mean and completely obvious at the 99th percentile. And I don't want you taking my word for that, so let's put a measured number on it. There's a paper called Etalon from Agrawal and colleagues, and their setup is worth saying slowly because every piece of it matters. They ran vLLM, and if that name is new to you, vLLM is one of the open source serving frameworks, which is the software that actually runs your model and hands the tokens back to your users. TensorRT, LLM, and SGLang are the other 2 you'll meet most often. And episode 2 walked through why all 3 end up the same shape. The model was E34B, an open model with 34 billion parameters served across 2 H100 GPUs. And the workload, real rxev summarization requests, so long papers going in and short summaries coming back, arriving at about 1.5 requests every second. That is not a stress test. That's a quiet afternoon. Then they measured scheduling delay, which is simply how long a request sat in the queue before anything happened to it. And for 60% of those requests, it came out above 25 seconds. So what is 25 seconds on the other end? Somebody hit enter and their screen did nothing at all for longer than most people will wait for anything. And how did that look on the dashboard? The metric everybody compared these systems with is called normalized latency, and all it does is take the whole time a request took and divide that by how many tokens it generated. Divide by tokens. Hold on to that. Because the median request in that trace produces 228 decode tokens. So spread a 25-second wait across those 228 tokens. And what lands in your metric? Roughly 110 milliseconds each, a 25-second freeze, arriving on your graph as 100 milliseconds. And notice that nothing broke here, right? Nobody misconfigured anything. The measurement did exactly what it was designed to do. And the design is what buries a 25-second stall. So does TPOT have that same problem? It divides by token count too. So yes, it does. And so does every other metric shaped that way. So what do you do about this on Monday? You plot both of them. Do you throw TPOT away? Not at all, because it's genuinely useful for your capacity planning and your cost per token, but put the 99th percentile of your intertoken latency right beside it and never read one without the other. And here's the rule I'd write on the wall. If every alert threshold you have is set on an average, then you have no alert on stalls at all. You'll find out from your users. One thing to watch while you're in there. vLLM's own metrics page puts both of those names onto a single histogram, calling it intertoken latency and time per output token on the very same line. So check what your tool computes underneath the label before you trust it. And do two different benchmarking tools even agree on intertoken latency? They don't, and we'll do that one properly in upcoming episodes. Now, the metric I watch people misread more than any other, and that's time to first token. Episode 1 told you it's Q plus prefill, and that's still true. So what I want to add isn't the definition, it's what happens the moment you compare your number against somebody else's. Because where do the ones you read actually come from? A vendor benchmark, a model card, a launch post? And what was that server doing while they measured? Almost certainly nothing else at all. On an idle server, your queue time is 0, right? So their time to first token is essentially just prefill, which is the fast and predictable half of it. Yours won't look like that. And is that your configuration being wrong? It isn't. It's that your server has other people on it. So treat a published number as a floor and nothing more, because the only one worth tuning against is the one you measured yourself on your own hardware at the arrival rate your users actually generate. And let's pay off what I promised at the end of last episode, which is the dashboard itself. Your end-to-end time is 3 things added together: queue time, prefill time, decode time. Keep all 3 separately, and your regression will stop being a mystery, because now it's a question with only 3 possible answers. Queue time grew, that's admission and capacity. Prefill grew, your prompts got longer or your batching changed underneath you. Decode grew, then you're into bandwidth and batch size, which is where we left episode 3. Every one of those has a metric name waiting in vLLM, and I've put them on screen rather than reading them out because names are for screenshotting. So pause here and take the picture, or better yet, note it down in your notebook. One last thing, and it breaks part of the model we just built. Modern vLLM turns on something called chunked prefill by default, which means a single batch can carry a decode step for your request and a chunk of somebody else's prompt at exactly the same time. We will cover chunked prefill in detail in the upcoming episodes, so stay tuned. So when you measure the gap between 2 of your tokens, what are you measuring? Not purely decode. You're measuring what your scheduler chose to do in that moment, with all the other traffic it was holding. So should you switch it off? Absolutely not. It's a good idea. And later episode around 21 is entirely about why. Just read your intertoken latency on a busy shared server as a scheduling number, because that's what it is. Before we finish, let's put these back on the table so they actually stay with you. Imagine somebody answering your question out loud. Time to first token is how long before they say their first word. Intertoken latency is the pause between each word after that. TPOT, your TPOT, is the average pace across the whole answer. And E2EL is door-to-door, your question through to their final word. So which one of those 4 is an average? Only the TPOT, right? The other 3 are a single weight, a gap you measure hundreds of times, and one total, which makes the TPOT the one that can look perfectly calm while somebody sits there for 25 seconds. If one thing from today survives the week, I'd like it to be that one. The Etalon paper is linked below, and it's worth your time for the full set of measurement pitfalls. Next time we take on throughput. And what do people actually mean by that word? 3 different things, so we'll separate all of them, along with goodput, which decides whether any of your throughput was worth having. And a piece of queuing theory called Little's Law, which will size a deployment for you in about 30 seconds on screen. See you there.